Shall I repeat it once again? Okay. Resolution is the ability to separate two different compounds, okay, or rather it is the ability to understand, or it is the ability to identify that two different spots on the chromatographic plate, okay, they are actually different. Okay, identifying two different spots as different. Okay, sometimes what happens is the spots may get merged together, they will overlap each other, and then you don't know whether the two, whether it is the same one spot or whether there are two different spots. Okay, so resolution, we have the formula for resolution like this: the distance between the centers of the spots. Okay, for example, if this is the case we are trying to understand, there are two spots here. If I calculate the distance, if that distance is say 1.5 centimeters, okay, 1.5 centimeters is the distance between the centers of the two spots, right? And if I calculate the average diameter of the two spots, that is the diameter of spot 1 plus the diameter of the spot 2 divided by 2, that is the average diameter. Is it okay? So this average diameter of the spots should be less than the distance between the centers of the spots. Is it okay? So just as an example, I take that the diameter of spot number 1 is 1 centimeter and the diameter of the other spot is 0.9 centimeter. So the total, so the average will be 1 plus 0.9 divided by 2. So it is 0.95. Okay. And the distance between the spots was 1.5. So 1.5 divided by 0.95, and that value is definitely greater than 1. Is it okay? So value greater than 1 means that the two spots are actually separate. There is good resolution between the two spots. On the other hand, take for example this case where again the average diameter is 0.95, okay, but the distance between the center of the spot, instead of here it was 1.5, but here the distance is 0.8, for example. Okay, distance between the center of the spots is 0.8. So 0.8 divided by 0.95, that is the average diameter of the spots, right? What is the value? Can you calculate it? 0.8 divided by 0.95. कोई करता है calculation?
0.5.
Point? नहीं, give me an exact value. 0.8 divided by 0.95.
0.84.
0.84.
84.
Let me try it on my mobile. Okay.
Yes, sir. 0.84 is correct.
0.84, sir.
Let me 0.8 divided by 0.95. 0.84.
94.
Right? Okay. So since this value is less than 1, okay, since the value is less than 1, we can say that the two spots are not clearly separated from each other, and therefore the resolution is not good enough. Okay. So what are we going to do now? If the resolution is not good, what should we do? Yes. If the resolution is
we should increase the polarity of the mobile phase.
Yeah, definitely. Either we should increase or we should decrease. It depends upon the type of the sample components. Okay. So by trial and error method, maybe you can do both. You can increase the polarity, you can decrease the polarity, and then you can find out whether it is having any effect on the separation of the sample components. Okay. So if you get better resolution in a particular mobile phase combination, then that combination you are going to use for your subsequent analysis. Is it okay? Okay. So then we go to the next slide. I don't know whether the font is clear to you. I'll try to increase the slide size. Okay, can you see it now? Okay. You don't have to, learn everything here by heart. This is just as an example. I'm trying to show you what are the different kinds of stationary phases used in TLC. It is aluminum oxide, okay, aluminum oxide cellulose, Then Kieselguhr is another stationary phase material. Silica gel. And in silica gel, there are different types. Okay, silica gel 60, silica gel 60, F254. Okay, these are all different types of gels based upon the particle size. Is it okay? It is just shown to you as an example of different types of stationary phases which can be used for TLC. Okay, and then this particular slide shows you how the ready-made plate looks like. I think I had one sample with me, but I don't remember exactly where I've kept it. Okay, so I decided to show you a image of this. Okay, can you see that there are two surfaces here? Okay, 1 and 2. One side is a polished side. Okay, this is the aluminum foil actually. Okay, so because of the metallic sheen, you can identify that it is an aluminum sheet. Okay, and that is not the side where you are going to do the chromatographic run, but the other side, which is coated with silica here or alumina. Okay, this is alumina actually. This is the side on which you are going to put your sample, and then you are going to carry out the chromatography. Okay, and in this particular image, you can see that the alumina plate, ready-made alumina plate, can be actually cut with a scissors. Okay, pair of scissors. So whatever size you want, you can cut out that size using a pair of scissors. Is it okay?
Yes.
Okay, then how about isolating the components in a pure form? Suppose you have done the chromatographic run, okay, you are satisfied with the run, and then just like preparative electrophoresis, you want to cut, in preparative electrophoresis, what we have seen, that we can cut out the gel, okay, we can crush the gel and we can obtain the purified sample component. So similarly, in case of the TLC also, you can scrape out that particular portion of the plate where your sample spot is there, okay, and then this can be put in a buffer and your sample material, your purified sample material can be obtained. Okay, so thin layer chromatography can also be used for preparative applications, and then especially where you want large quantity of the purified sample material, you can make the TLC plates more thicker. Okay, so for example, your adsorbent layer or your stationary phase layer could be 2 millimeter thick, quite a thick layer you can make, and then your sample components will be separated, and the purified component can be removed from the plate by scraping the plate, and you can obtain it. You can make use of that for your further application, or maybe you can go for further analysis. Is it okay? Then just as we have seen in paper chromatography as well as in electrophoresis also we have seen, we can have two-dimensional thin layer chromatography. Okay, so run your chromatography in one particular side, okay, one particular direction you can say, and then after the run is over, what you can do is you can remove the plate and tilt it 90 degree, okay, keep it again in a different mobile phase. You can look here, I have highlighted these words here, okay, different mobile phase is very important. So when you run the same plate tilted at 90 degree angle, okay, in a different mobile phase, then if there is a possibility that there are two sample components which are very similar to each other, they cannot be separated in one particular mobile phase, and in the other mobile phase at a different angle, you will be able to achieve separation of the sample components. Is it okay? Everybody, have you understood?
Yes, sir.
So,
This particular phrase is very important. Use a different mobile phase. In case of electrophoresis, we have used a different technique of electrophoresis. Okay, like in one particular electrophoretic run, we used say tube gel electrophoresis. Okay, and then in the other dimension, we have seen that we have used SDS page electrophoresis. Okay, or we can use isoelectric focusing. Okay, so combination of two different electrophoretic techniques together, that gives you more separation in two-dimensional electrophoresis. In a similar manner for TLC also, we are running thin layer chromatography in one mobile phase in the first run, okay, and in the second run we are using a different mobile phase, so that similarly placed components will be separated properly. Okay, then we come to another interesting technique in TLC, and that is called high performance thin layer chromatography. That is also called as HPTLC. Okay, so when we say HPTLC, we are actually changing the complete system here. We have an automatic, you can say, sampler. Can you see this here? First image at the lower portion. Okay, that is called
Yes, sir.
automatic sampler, TLC sampler. Can you see this part here? I'm showing it with the cursor. Okay, this one.
Okay, sir.
Okay, so that is actually a small, you can say, needle or a capillary. Okay, and that particular thing will take up your sample. Okay, a fixed amount of the sample can be taken up. For example, 2 microliters or 1 microliter sample can be taken up by using vacuum. Okay, and then this applicator will turn. Okay, and then it will go to the plate where, can you see the TLC plate here placed at the lower side here? Okay, so your applicator will take the sample from one vial. Okay, it will turn, and then it will place the sample on the TLC plate at a fixed location, at a precise location where you want the sample to be loaded. Okay, so that is an automatic TLC sample applicator or sampler. Once the samples are applied, now these samples which are applied are not in the form of a spot, but they are placed in the form of a narrow line. Okay, a very thin line of sample is applied. Okay, and then the TLC plates are kept in the chamber. Okay, now this chamber is also a very special chamber, you can say. I had this bigger image also here. By mistake, I tried to show you a smaller image. Okay, the bigger image is more clear here. Okay, this is a sample applicator. Okay, it takes the sample from your sample vial, and then it applies the sample in the form of a thin line on your TLC plate. Okay, the TLC plate also is a ready-made plate. It is not the manual plate, because ready-made plates will give you better resolution, because good quality material is normally coated on the ready-made plates. Okay, then you put your plate in the in the chromatographic chamber for the development. Now this chamber also is a special chamber because some kind of a gas pressure is applied, okay, in the chamber, and because of the gas pressure, the movement of the mobile phase will be faster. Okay, do you get what I'm saying? The movement of the sample of the solvent front of the solvent will be faster in this kind of chromatographic chamber because of gas pressure, and that is why it is called HPTLC. HP means high pressure TLC. Okay, so you are actually applying a high pressure, and the advantage of it is that your chromatographic time, your run time will be shorter. So for example, if your normal chromatography will take say half an hour or 1 hour, then this will be complete within 10 minutes or within 5 minutes. Is it okay? And then after your chromatographic run is over, the plate is removed from the chamber, and then it is put in another chamber, which is actually called as the scanner. Okay, so the scanner will scan your plate, okay, from one end to the other end, and wherever the sample zones are formed, those sample zones will be shown to you in the form of an image, right? And then you can see an image something like this. Can you see this, where HPTLC is written? This is actually an image which is obtained from HPTLC. Okay, you get very good quality image, very sharp images you can get. Not only that, but the machine has a software, and the software will help you to actually calculate the RF value of each and every sample component. Okay, so everything is done automatically. Have you all understood?
Yes, sir.
High performance,
Yes, sir.
performance linear chromatography. Okay, so this is an automated process, you can say. To the applications of TLC, there are a number of applications I have written here. Now in the exam, if it is a descriptive type of a question in the exam, then you are supposed to write about each and every application in slightly some detail. Okay, in some detail. Can you hear me? My internet connection is unstable.
Yes, sir, we can hear you.
ओके, प्रसाद जरा तुझ्या चिमण्यांचा आवाज बंद कर आता. प्रशांत. Okay. Okay, so TLC can be used to find out how many different components are present in a given mixture. Okay, it will also help you to find out the identity of the sample components. Of course, for this you need to run standards also. Okay, so you can compare your sample mixture with the standards, and then you will be in a position to identify your sample components. You can also follow the course of a particular chemical or a biochemical reaction. For example, if you are degrading pesticides using bacteria, culture of bacteria, okay, then after the degradation of a particular pesticide, what will happen? The pesticide will be converted into different products, okay, intermediates and the final product. So all the intermediates of the degradation can be actually identified using TLC, and therefore you will be in a position to find out what is the pathway which is used by the bacteria to degrade the pesticide. Is it okay? How many of you have not understood this? कोणाला कळलं नाहीये का? श्रद्धा, शीतल, सोनाली, शुभांगी, योगिता, कोणाला कळलं का?
Yes, sir.
ओके, काय बोललं मी सांगा बरं शुभांगी. काय समजलं तुम्हाला? Hello Shubhangi, can you hear me?
Yes, sir.
मग काय सांगितलं मी? How can you follow the course of a chemical reaction using TLC?
Repeat the question.
How can you follow the course of a reaction, chemical reaction or a biochemical reaction or a biodegradation pathway, for example, using TLC? एखाद्या पेस्टिसाइडचं डिग्रेडेशन कसं झालं हे आपण कसं बघू शकतो? I am in lecture right now. Okay.
Sorry, sir.
नाही कळलं का? ओके, मी तुम्हाला व्हाईट बोर्ड वरती दाखवतो. ओके, जरी थोडंसं आर्बिटरी असेल माझं, पण आय ट्राय टू एक्सप्लेन. ओके, सपोज यू हॅव अ पर्टिक्युलर पेस्टिसाइड. कुठल्या पेस्टिसाइड माहिती आहे तुम्हाला? समजा लिंडेन. एक मिनिट, टेक्स्ट टाकतो मी इथे. ओके, लिंडेन हे पेस्टिसाइड आहे. तुम्हाला माहिती आहे का सगळ्यांना हे? How many of you know it?
Sir, I don't know.
Okay.
Also, I don't know.
Chlorohexobenzene, hexachlorobenzene. Okay, linden is nothing but ज्याच्यामध्ये बेन्झीनची रिंग आहे. देयर इज अ सायक्लिक रिंग. ओके, and it has chlorine molecules attached to it. Okay, chlorine atoms attached to it, right? It is a very harmful pesticide, and therefore we would be interested in using a bacterial process for the degradation of linden, isn't it? आता मला पण सगळं इथे लक्षात नाही एकदम सडनली, पण आय विल जस्ट ट्राय टू टेल यू की त्याच्यामध्ये 2 पाथवेज असतात डिग्रेडेशनच्या. ओके, पाथवेचं नाव मी तुम्हाला आता सांगणार नाही, कारण मला स्वतःला ते लगेच इमिजिएटली काही लक्षात येणार नाही, रिकॉल करता येणार नाही. बट लेट अस से दॅट देर आर 2 pathways, say pathway X and pathway Y. Is it okay? And then using TLC, we want to find out which pathway is utilized by the bacteria to degrade linden. Okay. Now what will happen in pathway X? This linden molecule is degraded by bacteria in a particular manner. Suppose we get 2 compounds like compound A. A is an intermediate actually. Intermediate A. मी रब करतो. I don't know if I can move this. Yes. Intermediate A झाला पहिल्यांदा, त्याच्यानंतर काय झालं? Then there is another intermediate B. Okay. काय झालं? ऐश्वर्या आहे का क्लासमध्ये? She was out of the class for some reason. And then after this, suppose I get the product. Product is capital A, for example, or Z, capital Z. Okay. And then in the other pathway, for example, suppose I get another intermediate M. Okay, can you see this, everybody? Intermediate M. Okay, then I get another intermediate N. Then I get another intermediate O. Okay, and then finally I get the product. Product is, for example, capital Q.